Okay, I believe we are recording, so hand over to you, Javier, to present your slides.
Hi, thank you very much, Joanna. Hello, everyone. My name is Javier Almansa. For all of you who doesn't know me, I've been working at ARM for around 3 years now. So I originally started part of the TFA team, then I was moved to TF-RMM a couple of years ago. And I've been working on TF-RMM ever since. So in this presentation, I'm going to talk a little bit about the TF-RMM unit test framework, which is a sort of innovation we have introduced for RMM, TF-RMM or totally RMM. I'm going to go through this table of contents. So first, I'm going to introduce a new architecture that we've introduced, which is called a fake host architecture. And I'm going to talk a little bit about how it is implemented and how does it work, and I'm going to show a build and run example. And then I'm going to dig into the unit test framework on RMM. I'm going to explain a bit each architecture. I'm going to show a test example. I'm also going to build and run some examples showing the unit test framework in action. And finally, I want to finish. I'm going to talk a bit about coverage reports coverage support that we introduced in the framework. Although this last part is still work in progress, so there's nothing pushed yet. So without any further ado, let's start on the fake host architecture for RMM. So the fake host architecture allows RMM to support building and running the program natively as a regular user space application in the host machine. We achieve this by emulating the ARC64 specific parts of the program on the host machine by using hooks or callbacks in the program. So the implementation of these callbacks can differ based on the target deployment of the program in this mode. So for instance, the fake host architecture here can be used. Well, it can be used primarily for the unit test framework, but it can also be run as is without any unit test framework. And in that case, we will use different sets of callbacks or hooks to emulate different parts of the ARC64 architecture. So some of the features of this host architecture is that, as mentioned before, builds and runs the program natively. It is not intended to support multi-thread, although it can emulate different PEs. It cannot execute ARC64 instructions, assembly instructions for obvious reasons. The emulation for ARC64 exceptions in this mode is very limited. So we have some callbacks that are invoked natively when we try to emulate exceptions, but so far we've just implemented a bare minimum set of exception handlers. Also, the libc implementation for RMM cannot be verified with this architecture, as in this case, the compiler will link with its default libc implementation. Any questions?
Hey, Varun here. So
yeah, hi.
Hi. I have 2 questions about the emulation boxes that you have. So I'm just trying to understand a little bit better. So the hardware emulation box that you have, is it basically a simulator that you use, something similar to FVP or QMU that gives you this capability?
No, this is just a set of callbacks or hook functions that we link against the rest of RMM, and those emulate architectural functionalities. So everything runs natively on the development machine. There's nothing There's no FVP, there's no demo, there's no simulation. Everything is emulated and runs natively. So when you build on this platform, you end up with a binary that you can execute on your machine.
All right. Oh, okay. So then can we broadly think about these as just libraries that you hook into that give you these?
Yes.
Okay.
Yes, I'm going to dig into them in a bit.
Okay. Okay. Thank you.
Okay. Yeah. So yeah, moving forward. So the components for this host effect host platform. So this fake host platform is actually a platform layer. So all the platforms supported by RMM are inside a plat directory on the host directory. You can see the structure on the left side of this slide. So here inside the plat directory, we have a directory for FVP. So where we have all the platform components for FVP. Then we also have a host directory where we have all the host fake host components that will be built when we build for fake host. Also, if you notice on the upper part, we have a common directory. Those are actually parts that are common to all the platforms. And if you see inside the host directory, you will notice that we also have a common directory and another directory called host build. So this is because for the fake host architecture, we support subvariants of the platform. So far for the fake host, we only have a variant which is called host build. So this variant actually is the one that we use to build. It's the one that is built by default when we build fake host, and the result of this variant will be an executable that we can just run from our machine. So later, when we introduce the unit test framework, what we are going to do is to create another variant for the fake host architecture that will be inside the host directory as well. And this variant will be called a host test, and it will have a completely different set of test harnesses and callbacks, etc. And this will be the subvariant that will be linked once we build the unit test framework. So actually, this host build and those host harness and host setup are the equivalent to what it was on the previous slide, the hardware emulation layer, right? So those are just in charge of emulate all the components that we cannot run natively because we are running on a different platform. Any questions?
So just
can you go back to the previous? Sorry, go ahead.
Yes, go back to the previous slide.
Yeah, I'm just trying to understand why your hardware emulation is different from your AR64 intrinsic emulation. Is there? Why did you have to separate that out?
Sorry, I don't understand your question. Can you repeat it?
I'm asking why is hardware emulation separate from AR64 intrinsic emulation? Why is it not combined? Or why did it have to be separate logically?
Yeah, I think so.
Yeah. Probably I can answer. So the hardware emulation layer is emulating the system registers and the MMU aspects. So it's effectively the hardware IP. Whereas the intrinsic emulation is the instructions themselves. So for example, the barriers, the DSBs, the data cache operations, the TLBIs. So the instructions themselves are being emulated. So there's a difference over there, and hence it's two different blocks. Is that clear, Raghu?
Yeah, Yeah, I think I understood that part, but okay, maybe I need to look at the code closer to understand the value in it being different. But okay.
Yeah, it's only logically different. It doesn't in the code. So if you look at some of the architectural folders in RMM, within the architecture folder, there will be an ARC64 folder and there will be a fake host folder. And the fake host folder will do the implementation for fake host. So what happens is, for example, if you take an example of write to a system register, SCTLR EL2, there would be an implementation for ARC64, and there would be an implementation for fake host. And
Right.
fake host would just call into a callback, which is essentially being implemented by the host platform layer, which Javier just referred to previously in his fifth slide.
Okay.
Yeah.
Okay. Yeah. We can keep going, and yeah, maybe it'll click again. Thanks.
Okay. So yeah, moving forward, one of the things that we meant to explain here is, for instance, the fake host harness mechanism that we have. As Toby mentioned, this is where we have to emulate calls, register calls, etc. So in this case, for instance, the harness we have a harness implementation which is inside the host build variant of the fake host architecture. So you can see this on the right side of this slide. So and on the left side, we can see how the lib the realm library uses this purposes. So as an example, we're using the buffer component of the realm library. This buffer component, one of its public APIs is called granule map, which basically is in charge of getting a granule of memory and map it into the system so the system can use it. So this buffer.c is actually a common component. It is used by every single architecture in the system, every single available platform, such as fake host or FTP. And then granule map, when it's invoked, it will call buffer arc map, which is implemented in this other component, so buffer arc, which is an architectural component. So this lives in a folder inside the realm library, which is called either arc64 for arc64 architectures or fake host for any fake host variant that we want to build. So in turn, for the case of the fake host implementation, this then will call host buffer arc map, which is inside the host harness, which is part of the host build variant. So this is in the platform layer, right? Different. So when we build, for instance, with different variants, let's say later I'm going to introduce the host test variant. Instead of linking to this host harness, we are going to link to the host harness provided by the host test variant, which then it will have a different behavior, because for the unit test, we want this harness to behave differently. Maybe we want host buffer arc map to do something differently to what it does in this implementation. So this is the case of the fake host. For the case, for instance, of FTP, for FTP, we don't have harnesses. So in this case, what happens is actually that the architectural component, it will call back to another public API inside buffer.c, which will actually perform the granule mapping. So this is an example. So these are the same components. This is called buff arc. This is the version for fake host, and this is the version for FTP. So in the case of fake host, which is the one that I was showing on the diagram before, buffer arc map is so-called a host buffer arc map, which is in the platform layer. However, buffer arc map for FTP, it actually is defined as buffer map internal. So this is a public API, which is also available here in buffer.c. Just for information, host buffer arc map, which is in the platform layer, this actually performs some pre-processing of the parameters, then also calls buffer map internal, and then performs some pre-processing, post-processing of the return value, and then returns that back to the caller. Any questions? Okay. So another feature that is used by fake hosts is the ability to emulate sysrec accesses. So this way we can define what will happen when the fake host access to a different register, either for read or write. So for that, we have provided a set of utilities that allows to install independent callbacks for independent register access. So there are some other calls, but the main call of this interface is actually the one shown on the left side. It's called host util set sysrec callback. So this API receives as parameters the name of the register that we want to access, a pair of callbacks, one for read and one for write, and a value that will be used as a reset value for that register that we want to emulate. And here on the right side, we can see an example of register emulation. So this is actually one of the this is actually the code that initialized the fake host architecture. So here we can see that we call host util set default sysrec callback. So this API actually internally just calls host util set sysrec callback, but it just installed a default set of accessors that just access the value on return it or modifies the value on write. So for instance, if we see the last line, we set up a callback, a default callback for ACTR EL2, and we initialize this register to 0. So that way, when we call read ACTLR EL2 or write ACTLR EL2, we will be actually accessing the callbacks that we have installed. And that way we can control the values. So for instance, we can make, once we are running the unit test, we can make the unit test to check that we are performing a sequence of accesses into a specific register. We are storing a specific sequence of values, or reading a specific sequence of values, this kind of thing. So the way this works a bit more in detail is explained in the next slide. So we have, in order to define accessors for registers, we have this set of macros here, define sysrec read write functions. This is actually similar to what we do for TFS, right? So the specific case of it ACTLR EL2, which is the one that I'm going to be focusing here. So this defines a read accessor for ACTLR EL2. And this defines sysrec read function will actually create a function called read ACTLR EL2. And what this function will do will be just to call a callback called host read sysrec, and it will pass the name of the register that we want to access. And the way this works is when we invoke read ACTLR EL2, what we do is to call a component inside the host harness common library, which is called host read sysrec, and we pass the name of the register. Then host harness common we call another API called host util get sysrec callback, which is part of the host util. So this one will check if we have a callback installed for SCTLR EL2, and it will return a data structure called sysrec callback. This data structure, it will actually contain pointers to the read and write callbacks, and also a register value, which is the actual value stored inside that register. If we don't have any callback installed for this register, then we will return a new pointer. Then what will happen is that this layer again will just access that that callback that it just received. Will read the data, and the register value will be returned to host read sysrec, and this one will return the value. If we didn't have any sysrec callback structure, or we had this structure, but we didn't install a read callback, for instance, we only installed our read callback, then we will return 0, which is considered the default value if there's no callback installed. So this is the way we have to emulate sysrec access on the FakeHost platform.
So a quick question, right? So this all is this all is applicable only to FakeHost, right? So the real RMM read SCTLR EL2 will just translate to an MRS or MSR instruction.
Yes,
right?
Yes, exactly. So on the R64 architecture, this macro here defines sysrec read func and defines sysrec write func. They will actually create a different read SCTLR EL2, which will just use MSR instructions. It's actually implemented exactly the same as it is done on TFA, if I'm not wrong.
Oh, okay, all right. So this is all completely inside the FakeHost.
Yeah, this is all inside the FakeHost. Yeah. So if for instance we are running a unit test and we want that unit test to check that we are receiving a sequence, we are writing a sequence of values on arrays. So for instance, all we have to do is to write a function that every time it is called verifies the value and then moves an state in a, for instance, a state machine, and then that will be a callback for that register. For instance, so it's something that we could do. Another thing that we do with this is we use it to emulate different Ps. Because we store the CPU TF-RMM stores the CPU ID inside SCTLR EL2. So then we define a different SCTLR EL2 for each P. And what we do when we want to jump to one CPU or another, or emulate that we are running on one CPU or another, is just we modify the value of stored on that register. And then when the TF-RMM APIs called get my CPU ID, what we do is to read the SCTLR EL2 register that will give us the value that we saw before as a CPU ID. Another use that we have for this.
Just a correction, Javier, for the CPU ID we use TP ID.
TP ID.
Not this one.
Sorry.
Yeah.
TP ID.
Yeah.
Sorry.
Yeah, so effectively what's happening is it's possible for the host platform to expose any value as required back to the common RMM layer, and we are able to exercise different test scenarios depending on requirement. Yeah,
makes sense. Thank you.
Okay, so yeah, that was
does this mean at runtime, when a test is running, you can simulate multiple values for the same register? Or is it like that for one test case, one value for the testing register, and then you have another test case for the same testing register, but then in that case, you have a different value? Just wanted to understand your comment.
So what we can do, you actually are not limited here to what you can do. So you can reinstall a different when you start a different test, you can restore a different callback that will have a different behavior, or you can access the internal representation of the register by any other means you consider, and then when you when you call the read for that sysrec, then you will receive the value that you will read the value that you stored there by any other means, right? So it's actually no limitation. So you have a set of callbacks. You can modify those callbacks as you want. Those callbacks can access global data, and then another library can write or read this other global data. If you want another component of the test to modify that to simulate data corruption, for instance, you are actually not limited.
I see. And then the writer function for this global data would be outside the scope of this, or is it also part of your fake host architecture?
Sorry, I don't know if I got you. You mean the internal representation of the register?
Right. I think you said that internal for the register, you can always write to the global data and simulate different values that can be read by the callback later.
Mm-hmm.
So I wanted to understand this writer function for the global data. Is it also running as part of the host, the fake host, or is this something that's running outside of that, outside of this?
No, this is part of the fake host. So this utility library that implements the support for emulate the sysrec access on fake host is part of the fake host. So it is always built. And then when you call this API here, host util set sysrec callback, right? You pass the name of the register you want to emulate, and you pass the callbacks and a value. And then what happens internally is that this library allocates a sysrec callback structure, right? This sysrec callback has actually a pointer for each one of the callbacks, great and red. It also has a uint, uregister T data type where we store the value that is going to be stored or read, and it also stores the name of the register. So when we call the callback, so when we call the read API, for instance, what is happening is that we're calling that callback, and internally the host util library, what it does is to pass to that callback a pointer to the register representation, to that uregister T type. You can use that if you want to store your data there and then read the data from there, or you can have the data stored somewhere else, or you can create the data on the fly and then return that data on the fly there. So you actually you are actually not limited. You can use this in the way you want. You can just have a small register where you store the data, and all the PEs will see the same register. You can have a different register per PE, or you can just have the callback, maybe a function that will just perform some operation and return data emulating a reading.
Yeah, so you can both read and write. The fake host can override, and yeah, it's part of the same callback data structure here. That's very dynamic.
Okay, so yeah, that was pretty much everything that I wanted to explain about the fake host. I didn't want to go much into detail here. The next slide is actually it's actually a video in which I saw how we can build and run the fake host to see to give a demo. So I'm going to start the video. So the first step you can see here is just to call CMake to configure the project. We want to build the host, the fake host. So for that, we we pass the RMM config variables to the host dev config. We specify the source file, the source directory, and the build directory. This will configure our project. Then after that, we build the project, which is make build as usual. And once we have that, all we have to do is to call. So the build process will generate rmm.elf, which for FVP will be the binary that we want to load on FVP. But in this case, this is a binary that can run natively on a machine. So if we execute this binary, you can see here, we've just run TF-RMM. What we've done here was just to initialize TF-RMM and then it exits because we don't have support for receiving RMI commands yet. So here we can see, for instance, that we have put RMM, the RMM user interface, some information, the RMI RSI ABIs that we used when it was built, etc. And also, I want to note here this attestation init failed. So far, we don't have support for attestation yet on the fake host architecture. This is because at this point, when TF-RMM boots, it expects to receive an attestation token from EL3. But in this case, we haven't emulated that yet. So the attestation library will fail because it cannot find a valid token. But yeah, this is something that we will fix at some point. But yeah, the main point of this was how we can build RMM natively so we can run quick tests.
So quick question, right? Is EL3 emulated as well? You're not linking any BL31 or something like that, right? It's fully emulated.
No, EL3 is not emulated. This is only RMM.
So when RMM has to make EL3 calls, right, or calls to root world, how is that emulated? Is that again callbacks?
We don't have support for that, so it should be emulated using callbacks and hooks, but we haven't added support for that yet.
Yeah, so essentially the SMC calls, there is a emulation layer for the SMC calls, and there is a fake host interface which can be hooked to implement the necessary functionality. So all the SMC calls can be emulated within the fake host architecture, and essentially, yeah, we need to do what EL3 would have done in that instance. So for this particular case, when RMM boots up, it requests platform attestation key and realm attestation key from EL3. And what we need to do in fake host is put in a dummy token and format the packet as would be received from EL3 and return it back, and then the attestation in it would succeed. So effectively what we are seeing here is all the exact operations that would happen within RMM in ARC64 as part of cold boot, but it's running on the fake host.
Right. Okay. I think that answers my question. So you're saying that support is not fully built as of today, but that is the plan, right?
Yeah.
Is it partially built?
We need to add the token. Basically, we need to add the EL3 SMC layer, which essentially we need to add that. Yeah.
Okay. Thanks.
Okay, so now I'm going to move to the second part of this presentation, which is the unit test framework itself. So the unit test framework stands on top of the fake host architecture. As I mentioned before, it is actually a variant of the fake host. So let's say that we have one variant before that was host build, and now we introduce host test. So this is a component diagram, a small component diagram that shows how the unit test framework and the test are all related together. So the unit test framework and everything that is on its left actually belongs to the platform layer. So the unit test framework depends on the host test variant, which in turn depends on the fake host platform. It also depends on small library, which is a set of helpers for the unit test. We also use the test support included on CMake. We have another small library, which is actually quite tightly coupled to the unit test helpers, which are actually harnesses used for the unit test. And then we also make use of the CPP test framework. And then on the left side on the right side, we have the unit test, right? So for each component that we want to test, we will write a unit test. In my example, I'm going to explain how we implemented a unit test for the granule component inside the RMM library. So this unit test depends on the unit test framework and on the CPP test framework as well. It links both of them. And also the component and the test, which in this case will be the library that we want to test, as well as a set of test utils local to this library that we want to test, and a set of test harnesses that are also local to the component that we want to test. They all are linked together with the to the unit test, right? So these test utils and test harnesses differ per test. So we can have several tests for the same component, right? And each one of the tests will link to different set of test utils and test harness. Whereas the unit test framework will always link to the same test harness and test helpers that are part of the platform. So from unit test framework to the left is our platform component. From the test framework to the right, it is all component. It is all component dependent. Every component that we want to test, it will have its own set of unit tests and auxiliary files. Any question on this slide? Okay, then I'm going to move to the next one. So for all of you who don't know CPP test, so this is well, the unit test framework for RMM is based on CPP test. This is some sort of X unit test framework. It is based on C and C++. It's very simple, very easy to learn. It has a very small learning curve. It is very well documented, and it has a good set of APIs to exercise your interfaces. It's quite portable. And in the case of TF-RMM, we have introduced CPP test as we have added it as a kit module. So when we build the fake host with a build test subvariant, what happens is that the build system will automatically build CPP test, and it would link CPP test to the unit test. So we don't need to manually install CPP test or anything like that. The build system will take care of downloading the right version of CPP test for us and build it for us. So you can find more information about CPP test on the links provided here. Any questions? Okay, so one of the components that I mentioned before was the test helper. This is a very small library, which is part of the host test variant. At the moment, it only has a couple of APIs that we can see here. Test platform setup, which performs some basic initialization of the fake host architecture. And we also have another API, which actually returns the number of granules supported by the fake host, because this is actually an API that is not available on TF-RMM because MCP platform doesn't use it. So it is very limited, but we can add extra functionality to this API as long as we need it. Okay, So next is a small text example. As mentioned before, we're going to focus on explain how to implement a test to a unit test to exercise the Granule API of the Realm library. So we can see here on the right, that we have the library directory, and inside we have the Realm library. So inside the source of the Realm library, we would have the granule.c component, and what we are going to do here is to test its public API. We are only focused on the public API. We are not focused on any internal API, only the external one. So for that, we create a directory called test, right? And this is where we are going to store all our unit tests and any ancillary files that we need to for the test. So in this case, we have Granule CPP, which is where the unit tests are going to live. And CPP utest actually uses CPP utest actually uses C++, so the unit test have to be written in C++. Then we also have, for instance, so the mentioned before, the test utils that I mentioned here, right? So those will be here, test utils. And if we need any test harnesses, they will be here. And I'm going to explain a little bit how all this work, and I'm going to show flow diagrams on how the test harnesses work, right? So something that is also important is that we need to update the CMake list TXT file in order to add support for the test. This is done, as you can see here. So in order to add unit test functionality, we need to call inside the CMake the CMake file. We have to call to RMM build unit test. So this is a CMake function that we created as part of the unit test framework. So it takes a number of parameters. Some of them are shown here. So one of the most important is the name of the test. This name must match with the name of the test group in the unit test. For all of you familiar with CPP utest, you know that the tests are grouped. And so this granule here, this one here must match the test group on your unit test. Then this is the library where we want to link this test. So we are testing actually a component of the Realm library. So the target will be RMM libRealm. And these are the sources that we need to build for our test. This will be Granule CPP, the test utils, and the test harness. And this is this here iterations. This is an optional parameter that we can use to specify how many times do we want to run the test. So we can like run a stress test. For instance, if we can, if our test access random granules or random positions of memory, we can get here a high value, so we can sort of emulate or run stress test. This is like an optional parameter, is not needed, but I just use it here as a support. Okay, so the next slide just shows an example of setup for the granule test. So as I explained before, we have the test group here, which is granule, which matches with the name of the test. Yeah, we have our test setup. So each test can have its own test setup. It is not mandatory that all the test setups are like this. So in this particular case, what I do is, if this is the first time that we run the test setup, we just initialize RMM. Then we set the current CPU ID to 0. We initialize the random seed using the time for that, and that will also be a mark or flag to know that we have already initialized. And then for every test, we make sure that we clean all the granules. And this is all setup, but again, every test can have its own setup. In this case, we don't need to perform any teardowns, so the teardowns here is empty. And then the next example is on the granule test. So here are two examples of exercising the fine granule API inside the granule library. So we have two different test cases here. So one is to get a random granule and verify that its physical address corresponds to the expected one. So we run this test here and we perform other checks here. And the second test case will be to try to get a granule for an unaligned address. And as you can see, this is expected to give us a null pointer because we cannot get a granule for an unaligned address. So here for every single test case, even if it is for the same API, but every single test case, our convention will be that we will define a different test. So we have the test for the granule group, and this will be fine granule TC2, and this will be fine granule TC1. And if we have to test more use cases on the same API, then we will have TC3, TC4, and so on and so forth. And again, each test depending on the API that we want to test and how do we want to test it. Any questions? Okay, so here I think it's a very important part to understand how the test harnesses work. So remember that before I explained how the test harness, how the harnesses work for the fake host platform when we were using the host build variant. Remember that in that case, I'm going to go back so you can see it again. So yeah, so if you remember here, a granule map called buffer arc map, and then here in turn called host buffer arc map, right? And this is part of the host build. This is part of the host build variant. So in this case, we move forward. Here we are. So in this case, the harness in this case it belongs to the host test variant, not to the host build. And the first part of the call to granule map is quite different. It's quite similar. So we call granule map. This is called buffer arc map, which is part of the architectural component. Then this calls the harness. But in this case, host test. The host test harness will call the test harness, which is part of the realm test library. So remember that I explained before that again, but I want to make sure that we understand this. So we have a test details that I explained before. So this now will be the test harness that we have that belongs to the unit test that we want to run. So in this case, the harness, this is on the platform layer, will call this test buffer map, right? Which is part of the test. And this will be the one who will perform any activity we need to do in order to do a granule map. Then it will return its value to this one, to the platform harness, and this one will forward the result back to the caller. So if we have different tests, then we can have different harnesses for different tests. We need to modify the behavior of these harnesses. So at the moment, test harness.c is linked statically. So we cannot modify this. We cannot have different harnesses for different tests in the same group. But one of the improvements that we have already on our backlog is to add support, so we can install callbacks dynamically to install different test harnesses here, right? And so there's also the host test variant has an API which is, must be implemented by this source here. Any question about this? Because I know this can be very confusing. Okay, so then to finish, well, not finish yet, but to finish this section, I'm going to show an example showing how do we run the unit test on the host machine. So it starts as before with configure our project. We will use the host test config, but in this case, the host variant that we specify will be host test. If we don't specify host variant, it will be host built by default. But here we want to run unit test, so we have to specify variant. We build a project, and if you noticed, we are building, we are building CPP unit test. Well, it's not here. Now we build the project, and then CPP unit test will be built as well. Yeah. So this step has already built CPP unit test, has built a RMM, has linked everything together, and has generated another RMM.elf binary. However, in order to call the unit test, we use the CMake test support. So CMake will actually have created a set of rules that will run the test for us. So in this case, that's called make test, and we pass the directory, and this will run all the tests for us. So far, we only have test for the granule library. It is repeating the test 1,000 times, and then after 5 seconds, it finishes, and it gives the result that all the tests have passed. Now, because so we can execute the test using CMake test framework, but we can also run the binary independently. So this is an example. Here, what we do is to build called RMM-elf. So this is actually a CPPU test binary. So the first thing that I'm going to do here is to call the help menu, which is the standard for CPPU test, for any of you familiar with it. And then, for instance, what I do here is to call RMM-elf and specify that I want to execute the granule group with verbosity enabled. And as you can see here, this will give us, this will execute all the tests, all the test cases that we have here, and will give us the result. Also, notice that because we have the notice verbosity enabled on RMM, we also have the welcome message on RMM. If we had enabled like verbosity level, then we will see all the debug and verbosity messages interleaved with the test as well. But I mean, in this test, we don't need that. It's not just an effect. Okay, any questions so far? Okay. Also, something that I think is worth to mention is that when we run the test using the makefile rules that created by CMake, we will generate log files. Those log files are stored under this path found here. So if we have a log level enabled with high verbosity and we repeat the test a large number of times, be aware that this can cause that the test will run very slowly, and also this file can be very, very large. So when I was debugging the feature, I ended up having a 10 gigabyte file that wasn't very, very usable. But yeah, that's the point that we also will have a log here that we can use to debug if we find any problem. Just to finish, also, I wanted to show you a feature which is currently under development. Although we expect to be able to push these patches externally, maybe by tomorrow or by beginning of next week. So all the fake host architecture, one of the reasons why we implemented that is because we wanted to make sure that we have very good coverability test on RMM. So one of the things that the unit test allow is to enable coverability, is to give a coverability information. So here is an example of the coverability results for the granule unit test. So we can see, for instance, that the granule.c file has been 97% of the lines have been tested. 98.9% of the lines of the unit test have also been executed. This is an HTML report, but by default, the tool will generate XML reports that could be used by Jenkins. So we can add this as part of the automated CI. So every time we push a patch, CI will run coverability, will run all the tests, will run coverability tests, and we can also see a report on the coverability. Just mention that the number of branches tested here is relatively low because we don't have yet support to emulate panic and exception. So all the paths that lead to panic and exception inside the code and the test hasn't been tested. So that's the reason why we don't have many branches tested. But again, this is also a feature that we can we expect it to continue. So we can emulate panics and exceptions and specify the default behavior, the expected behavior for them. And that was the end of the presentation. Do you have any questions?
Yeah, I had a quick question, Javier, on the previous slide. So is that actually using coverability tool, as in Synopsys coverability, or is that just a standard GCC coverage
It's
tool?
the standard CCC coverage tool. Something that I forgot to mention is that the unit test framework and the coverability report will both be supported. Will be supported in both GCC and CLang. So in this case, this was done with Zcov for GCC.
Okay, yeah. Then I suppose that maybe the slide should be corrected, because I think coverability is really the name of the tool from Synopsys, which might be misleading here. Maybe coverage report would be better.
Yeah, yeah, you're right. Yeah, I will update that then. Yeah, good point. Thank you. Yeah, coverage report, no coverage. I will update this before we upload the slides. So anyone else have any more questions?
Yeah, I have. I mean, we are at the top of the hour, so I have some questions. Maybe I'll just ask the obvious one. So first one is, how do you plan to use all of this information for your code reviews, if at all that's the plan?
I don't know if I understood your question.
So for code reviews, when someone pushes a new change to the RMM, how do you plan to make use of all of this?
So we expect, and this will be part of the documentation, because as part of the patch stack with all the unit test framework, we will also update the documentation. So what we expect is that if there is a significant change on an existing component or a new component, say a new library, we will expect that unit test for those changes, for this new library or for this new API on an existing library, will be added. Depending on the size, this could be added as a separate test, as a separate patch, or in the same patch. But yeah, our objective is that so far we only have two components that are tested, which is the buffer component and the granule component, both of them on the Rare library. But our objective is to write unit tests for every single component, and any contributor will need to make sure that if they make the content changes, they have updated or added unit test to cover the changes.
Yep,
With-
and sorry, just to add on to that, we also plan to add some kind of CI such that the CI will run the coverage, the unit test, and it can get the XML report from the coverage. And for if the patch which is contributed is bringing down the coverage, we can flag it up in the CI, and we can take appropriate action.
You've answered my question before I asked it, Sobi. Thank you.
Okay, yeah, thanks.
So on a principle or a philosophy level, I just wanted to understand the test case generation approach that you have followed for this project. So when you created all these test cases for this component, did you look at the code and then created the test cases, or you looked at the requirements and then created the test cases? How was it?
In this case, in this particular case, I try not to look at the code. So usually what I was looking was at the description of what the API has to do. I try not to look at the code because that could taint my implementation. The idea will be to have some sort of driving development test, although that can slow down the process a lot. The convention will be just to use your judgment. I mean, the patches will be tested as well. Sorry, the patches will be reviewed. Your unit test will be reviewed. So if you miss something, it's probably going to be caught up. But for every single, also the coverage test will check if you miss any path, if there's any code or any branch that you haven't executed, and that will give you a clue of something that you have missed on your test.
Yep. So effectively, we want to cover all the lines of that particular API. So the primary criteria is, does your unit test cover more than 95% of lines of that particular API? That would be the primary criteria. And then any further additional tests that you add, it's just more tests that we review and take it in.
Also, the test to be the source code for the test to be very well commented. If we decide to skip a test for some reason, we should explain why, because we want to make sure that there's no misunderstandings between the specification of what the API should be doing and what we are testing. Because so we have to make sure that we know what we are testing and we know what this should be doing. So we are not testing the wrong behavior.
Okay, so if I didn't understand the entire bit, but so what you guys are trying to say is the test cases are basically generated from the spec and not from the code. So that's the understanding in a nutshell. Is that right?
Yeah, I mean, it depends on the component. As mentioned before, you will need to use your judgment. But yeah, ideally, there should be the test cases to come from the specification when possible. Yeah.
Right.
So so just to be clear, the unit tests are testing units inside RMM. So not necessarily, these are not part of the RMM specification as such produced by the ARM architecture.
We're talking about the component specification, the library, the API specification, the internal API specification for that specific component.
Yeah. So effectively, there is a function documentation for every component API, and we go by that and try to test against that. Yeah.
Right, but those component specifications would finally also originate from the spec. I mean, the spec is what is driving the entire architecture, and then the architecture is broken down into smaller units. So eventually everything should be traceable back to the architecture. You won't have a unit that just lives by itself, that has no purpose when you look at it from the spec perspective, right? It's trying to implement some kind of function that is driven from the spec. So
so the spec will specify the high level behavior and rest is implementation, and the components are implementing aspects of that spec. Yeah. So in that manner, you could possibly trace it to some aspect of the high-level RMM specification. Yeah.
But is that done? I mean, what I'm hearing, I'm a little bit worried with the approach that was taken with the test case generation. I mean, looks like, I think someone's, maybe you or Javier, someone said that the main criteria is the line coverage. I mean, that should not be the main criteria. The main criteria should be the functionality, and how, if that functionality is, are we covering the requirements? I mean, that should be the main thing. And then second question that I had is, so when you generate the test cases, are these manually generated, or again, is there some kind of automated tool that
No, you have to write the test manually.
Okay, I mean, writing the test is fine. Just trying to understand the test cases. So the test scenarios, let's say,
Again, the test scenarios will depend on the APIs that are on the library you want to test. So in my case, for instance, when I wrote the unit test for the Granule library, I just went to the header file of the Granule library, and I just went through all the public APIs and I started writing tests for them. And I figured out what would be the behavior for each one of the APIs and under different conditions. So if we pass an unaligned address, if we pass an address out of range, if we pass a valid address, etc. And then I just wrote a unit test for each one of them. Then I ran the coverage test to make sure that I covered all the APIs and on all the possible paths in the APIs.
Yeah. So even though we are referring to the spec to generate the initial level of tests, the coverage is a good indication that you have written enough test cases to cover all aspects of the function behavior. Because these are internal functions, not all corner cases of the function may be captured as part of the function documentation. There might be some implementation specific corner cases. So yeah, the documentation is not perfect. Hence, I would think if the test manages to cover most of the function lines of code in that function, it's probably covering most of the intended cases for that API.
I mean, that would hold true if you have a mechanism to prove that the functionality that a unit implements covers the requirements that were allocated to it from the spec. Unless you can prove that, unless you can make that argument, you cannot 100% say that, oh, even though I have now that I have 100% coverage, it covers the entire requirement. You can have 100% coverage, but still only implement 50% of the requirement. So, I mean, that coverage argument doesn't hold on its own.
Yeah, it's kind of a mixture of both cases, because now one aspect of the fake host architecture is you're building the entire RMM as a single application. So the API is actually working on the set of intrinsics which are emulated for that application. So if the functionality, for example, if you're mapping a virtual address to a physical address, right, that functionality is being emulated within the RMM binary for fake host. So it's intrinsically testing the functionality, and because the primary objective is to make sure that the internal functions are being tested properly, because many of these internal functions cannot be reached from the SMC interface that we have. So that's the primary intention here.
So I think this kind of test is more about verifying that the code is working as designed, and not verifying whether the design is fulfilling the requirements.
Yeah, that's what.
Yeah, it's a good point. Yeah, thank you, Georgie.
Right, and I think we need a change in philosophy and approach to actually think about if a unit, look at it from a different way, instead of just looking at, is the design getting covered, or sorry, is the unit covered, and instead of looking at it from way where we say that, is the unit actually fulfilling whatever allocated to it. So That's what I think I was trying to get at.
Yeah, so I think for requirement verification, it is better to have system tests which are executed on the real target and so on, because unit testing is separated from the real use case. So the code is executing on a different architecture in an environment which is much more resourceful than the target environment will be, and so on. So inherently there are limitations to this.
True, true. There are limitations, but then a unit by itself cannot exist without having requirements or some reason for it to exist. And then the reason comes from the top level requirements. So we cannot say that the unit exists in isolation without, and then we cannot look at it from a requirement point of view. Of course, there will be implementation details, and that would mean that a top level requirement is decomposed into multiple further requirements that reach the unit. So there has to be a link. There can never be a unit that exists in isolation.
Yeah.
Well, I think if there's no more questions, shall we finish this meeting?
Yeah, sure. If there's no more questions.
Just let me add that so this link here shows the TF-RMM Read the Docs documentation is now available online. So you can find instances there on how to join the mailing list, how to download the code, how to contribute the code, information about the RAID architecture, and some more interesting stuff there.
And I believe a project page will appear soon on trustedfirmware.org.
Mm-hmm.
Is that correct? Yeah, I think you guys are working on one to make
yeah, I think so.
Yeah, so it'll be another like TFA and Hafnium and all the various other good projects that we had. This one should be shareable at some point once the page is put together.
Yeah.
All right. Thank you, everyone, for your time. If there's no other questions. No, if not, I'll finish the recording.
Thank you. Bye.